Okay, so like I mentioned before, we are continuing our discussion of the fundamental properties of nonlinear normal modes. Last time we looked at just this 2-degree freedom system shown here. We are going to look at that system quite a lot throughout the rest of these notes. And towards the end, we'll look at a couple different systems as well. All right, so here are some of the frequency response functions that were computed for this system, and this just shows how both of the modes, they depend on their amplitudes change based on the amount of energy in the system, and you get this bending of these FRFs. All right. And we also looked at how that energy dependence shows up in the configuration space. And then we did our second worksheet. So an important remark is that the energy dependence of the NNMs prevents the direct separation of space and time in the governing equations of motion, and therefore this makes calculating the NNMs analytically much more difficult than, say, linear normal modes. All right, so we're going to take a look now at what are known as frequency energy plots. These are depictions of how nonlinear normal modes, how their backbone branches or frequencies change with respect to the energy in the system. What's shown here is just a linear system. It's the same system we looked at previously in last time and in worksheet 2, with the nonlinear term just cut off and removed. So in that case, you have two linear normal modes, which are energy invariant, so they don't change with energy. And if we plot those on a frequency energy plot, we just get straight horizontal lines because their frequencies don't change. And then if we look at their modal curves at different energy levels, we'll find that they're exactly the same because those are also independent of energy. Okay. Nothing really special or interesting there, but just wanted to show that here. Oh, and this is taken from a paper by Kirshen et al. Shown here. A lot of the plots shown here will be taken from that paper or various papers as well. All right, so if we add back that nonlinearity and then compute the nonlinear normal modes, these are computed using a numerical continuation method, which you won't be expected to know. I'm more interested in you understanding the basic fundamental properties of these and how they change. And then when we look at like experimental data, we'll start to observe how we can identify these nonlinear normal modes from things like the wavelet transform, for example. Okay, so again, this is that same system we studied on Tuesday. In this case, we're plotting the backbone curves for the two nonlinear normal modes. The naming convention can be kind of obtuse at times for these. So we might just call them NNM1, NNM2, NNM, etc. For this particular system, they've called them S11 and S11 plus and S11 minus, where the S stands for symmetric periodic solutions. The 1,1 means that each mass oscillates with the same dominant frequency, so they're both oscillating with the same frequency. And then the plus or minus means in phase or out of phase. And if you read other papers by other people, they may change the definition of these and what they label these as. I like to just say NNM1 or NNM2 because it goes back to the idea of there being 2 degrees of freedom and associated to that. However, as you've seen last week and in your homework, there can be more nonlinear normal modes than there are degrees of freedom, and so that does complicate things at times. Okay. So, like I said, these are the backbone curves or backbone branches for each of these. So when we did multiple scales, we computed the backbone branch for a couple different systems where we were able to plot that as a function of amplitude versus frequency. These are very much the same as those, except now we're plotting them as frequency versus energy, as shown here. And in this case, you can see how the modal curves change with respect to energy, and they're towards very high energy, you get a localization of the response in 1 degree of freedom versus another, which is something you found in your analysis of worksheet 2. So then the question is, the response shown here, is this response a nonlinear normal mode? Just take a moment and think about that, and what, if you think that's a nonlinear normal mode response or not.
So what does this present?
Yeah, so on the right, on the left is the time response of the system over a single period.
So one of them is x1, one of them is x2?
Yeah. And then on the right side is the modal curve for that. Yeah, and I say one period, and that doesn't necessarily need to be the period of a single n and m. It could be some combination. But the key thing is that this is a periodic response, and it takes a time of 20 seconds, in this case, to start back where it began. All right, any guesses from? Yeah. Depends on your definition, I would say.
First of all, it's definitely not similar.
For sure, absolutely. Yeah, so if we move on, what we'll say is that, this is a periodic solution, but it is not synchronous vibrations. So if we go by Rosenberg's definition, then it's not a nonlinear normal mode. But given the fact that it's periodic and it will just repeat like this for all time, that gives you some physical reasoning that this should be considered a nonlinear normal mode based on this idea of we're seeking periodic solutions to those equations. All right, we're going to come back to this problem in the sense of, is Rosenberg's definition complete, or does it need to be modified after we go through the next fundamental property, which is a discussion of modal interactions or internal resonances between the N and M's. All right, so we're going to again consider that same 2 degree freedom system that we've been considering, where we were studying in the previous section. And what we'll end up being able to find is that you can realize a countable infinity of internal resonances or modal interactions. And so each of the nonlinear normal modes will have harmonics associated with it. So oscillations that occur twice, 3 times, 4 times, etc. Its frequency as well as superharmonics as well. And as a result of that, because of those extra harmonics, we can end up realizing some commensurate integer relationship between the 2 nonlinear normal modes, which then leads into the internal resonance, which we studied in the multi-degree freedom system with multiple scales. All right, so if we continue to compute the nonlinear normal modes for that 2 degree freedom system and go up to higher energies, what you'll end up with this kind of weird shape thing that pops out. We call these tongues. So I've lost my laser tool, so I'll just draw a little circle. So this guy right here, this right here, that is what's known as a tongue. So there's a couple things we should observe here. First of all, at the particular energies where these tongues arise, we end up with multiple solutions that could appear, which tells us that that means that there is not a unique solution to the governing equations like there would be for a linear system. And it also brings into question about the stability of the different solutions, which we will address in the next section. So what we've done here, and you can see I've labeled these as NNM1, NNM2, just for simplicity here. What I've done is I've taken the frequency of NNM2 and divided it by 3 and projected it onto this as the dashed red line. If we zoom in on that tongue, what you end up finding is that exactly at the tip of the tongue, like right here, it touches that dashed red line. And that's how you can tell that this is now a 3-to-1 subharmonic tongue where the first and the second NNMs will resonate with each other. We will study effects like these using data towards, well, in like the middle of the data-driven portion of the class. We will look at experimental results and combine our analytical tools with some data-driven tools and then identify resonances directly from measured responses. Okay. If we take a zoomed in view of that subharmonic tongue shown here, and I'm not sure I labeled these things here. Actually, hold on, let's go back a page and add some labels. All right, so we again have this S11 plus branch in black. We have the S11 minus branch in solid red. This little gray box down here, this is where our subharmonic tongue is. If we go to our zoomed in view of the subharmonic tongue, we still have S11 plus in the lower portion of it. And in the upper portion, we end up with what's now 3-1. And so that tells us that up here at least, along this top branch, the first mass is now oscillating at 3 times the frequency that the second mass is oscillating at. And we're going to see that in a moment when we look at the configuration curves, and also when we look at some of the actual periodic solutions. Okay. And this dashed red line, we can call this S33 minus.
So when the ratio is not 1, when there is no plus and minus?
Yeah. According to that paper by Kirshen et al., you could make an argument that the upper branch should be like a plus and the lower branch should be a minus, but they don't go into that much detail, I would say. The key, and I'll show a frequency energy plot where there are dozens of tongues, and then the labeling becomes very obtuse and hard to understand what's going on.
So what does 3-3 means?
So in this case, it's still this out-of-phase Mohs, but we've effectively divided by 3, and so as a result, both of the masses will be oscillating with 3 times in one period, effectively. And they're both oscillating at that rate. Okay, if we take a look at this zoomed-in view here, what I've done is I have plotted the modal curves as we move along here. And we're just going to briefly label these guys. So we'll call this one right here case 1. This is case 2. Then case 3 is up here. We have case 4, case 5, 6, and then 7 is over here. So as we move along this tongue, the modal curves are becoming progressively more and more complicated in general. We start off with in some sense a similar, well, it's still not similar, but it's at least a one-to-one correspondence in case one. Same in case two, there is a little bit of a case where it's no longer one-to-one anymore. And then case three and beyond, they lose this one-to-one correspondence between the two masses. And a really interesting and important feature is that in case five, we suddenly get back what looks like the out of phase mode. And this is where we would say that this is a mode conversion. Where the first NNM now behaves like the second NNM in the sense that it gives an out of phase motion. Okay, let's take a look at some of the periodic solutions here. Here is the periodic solution for case one. On the left is the actual modal curve. On the right is the periodic solution, is what we would call it. So in this case, there is still only one oscillation in each mass per period, although they're not necessarily, well, they are synchronous in this case, but they're not simple sinusoids, is what I would say. If we move to case two, again, we start to see, the loss of the one-to-one in the modal curve, and from there, the periodic solution is going to get more and more complicated. Case three is where we start to have this kind of S-shaped, which is very much associated with resonances between masses and modes. In case four, you can start to see how we now have three oscillations in the first mass, which is the black curve, and only one oscillation or one cycle in the second mass, which is the red curve shown here. So that's where this 3-1 comes into play. So if we come back up here and look at case four again, we're again on this 3-1 subharmonic ton, and 3 means that we're getting 3 cycles in the first mass to every 1 cycle in the second mass. If we go and look at case 5, which was where they're out of phase, we have this mode conversion. In this case, we again get 3 cycles in both masses in a single period. And that's why it's this S311, or S33 is why we call it that curve. Take a look now at case 6, and I'll just scroll up briefly. Case 6 is now on the lower branch of the S31 subharmonic tongue. And in this case, you can see that again we're getting this 3 oscillations in mass 1 for every single oscillation or cycle in mass 2. However, in this case, unlike case 4, they are starting with opposite signs. And that's where I would say you could argue that the lower branch is S31 minus and the upper branch is S3 plus.
So can you, is there a way to say that the behavior is periodic by just looking at the mode or the configuration graph?
So is there a way to determine like the number of cycles per period?
Or like at least to know that it's a periodic.
Oh yeah, these are all periodic.
But now we know it's periodic. We just, like if you give us just one of these figures, like the x2, x1 figure, one of these, and it asks us is it periodic or not?
Yeah, it's a tough question. Likely not.
Okay.
It would depend. I mean, for something, you know, like case 5 or these cases are shown here, probably. For if it's, well.
Yeah, so let's say what's another way, like, is it possible to get one of these shapes that's not periodic?
Yes, and you can get very complicated shapes. But the key thing is that when we're solving for these NNMs, these are periodic by definition. That's the crux of our definition of what a nonlinear normal mode is, that it's a periodic oscillation. It doesn't have to be synchronous, but, well, we're going to get to that. Right now, Rosenberg is a synchronous periodic oscillation. We're going to modify that to just be a not necessarily synchronous periodic motion. And so the numerical tool that is used to compute these NNMs is actually looking for periodic solutions. So it's making a prediction of what the frequency should be. It's then doing a short simulation to see if it, is a periodic motion, and then it adjusts the frequency using a continuation, like a predictor corrector approach.
So the key word is like we're looking for periodic.
Yes. So that is the key thing here. So that doesn't mean that all responses that you can find in a nonlinear system are periodic. Even for very simple systems, they can be aperiodic or quasi-periodic. In this case, we are specifically looking at the nonlinear normal modes, and the tool is actually specifically looking for these things. That also doesn't mean that it's necessarily easy to compute these nonlinear normal modes, and we'll see some of the frequency response or frequency energy plots that I produced where I wasn't able to extend past a certain energy for a particular mode. Just because the solver wouldn't converge. All right. Okay, so yeah, when we get back to, in fact, I missed something, so let's go and label these. So in case 1, we're still on S11 plus. In case 2, we're still S11 plus. In case 3, we're on S31 plus. Yeah, I'll add the plus here because these are in phase. And then whatever in phase means. By that I really mean they start with the same sign and they end with the same sign. That's really what I mean here. We're still on S3, S31 plus. And since they're oscillating at different frequencies, in phase, out of phase doesn't necessarily make sense. That's really why you don't typically see it. So in case 5, here we have, this should be an S33. Case 6, you could say is S31 minus, and here they're starting with opposite signs, but they're not necessarily oscillating in phase or out of phase. And then the last case 7 goes back to S11. All right. Okay, so if you look at the ratio of the linearized natural frequencies, it's actually square root of 3. But we're still able to realize a 3-to-1 ratio here between the two frequencies because the frequency of the first NNM will increase less rapidly than the second NNM, such that the second NNM grows faster. If we go back to the FEP, shown here, you can see that S11 minus branch just blows up there. And as a result, you're still able to achieve this 3-to-1 ratio, even though the linearized ratio of the linearized frequencies is square root of 3. And so a key thing here is that this shows that the NNMs can be internally resonant without necessarily having commensurate linear natural frequencies, which was kind of the underlying requirement when we looked at internal resonance in multi-degree freedom systems using method of multiple scales, which was again for weak nonlinearity, and here we're looking at strong nonlinearity. So strong nonlinearity allows for internal resonance between NNMs regardless of what their linear natural frequencies are. However, if their linear natural frequencies are close to a commensurate ratio, then you get these internal resonances at lower energies. And so one thing you can do in an experiment, for example, if you want to achieve a 3-to-1 resonance, you can design the system to have a ratio of like 3.25 to 1 for the linear normal modes. And then at a lower, relatively achievable energy, you can realize an internal resonance between the modes. And it's also not just like 3-to-1. You can have things like, in fact, when we do the data-driven stuff, we will just find a 5-to-2 internal resonance between two modes. So it doesn't necessarily have to be n-to-1 or 1-to-n. It can be any kind of integer ratio. That being said, if for example, depending on the type of nonlinearity, if it's like a hardening type of nonlinearity, then the frequencies are only ever going to increase. So if your ratio between the linearized natural frequency is let's say above 2 to 1, then you really won't be able to achieve a 2 to 1 between two modes in terms of physical experiments. Theoretically, they will still exist, but you may not be able to achieve that level of energy in an actual experiment without breaking something. And so there are at times, if you're trying to study resonances, there are at times design considerations that need to be made. Now, if you're trying to design a system to have an internal resonance at a particular ratio, you do need to be aware of what their linearized frequencies are. Okay. All right. And so, more importantly, these results demonstrate that this important nonlinear phenomena can be missed when resorting to perturbation techniques like method of multiple scales, averaging, etc., which are only limited to these small amplitude motions. So if you were to apply, let's imagine we had a weak nonlinearity, and you were to apply the method of multiple scales, you would find that this 3 to 1 internal resonance doesn't exist because the linearized frequencies don't have, because their ratio is square root of 3. And so that is why things like the method of complexification averaging are so useful for studying strongly nonlinear systems. And if you keep computing that first NNM, you end up with many, many more internal resonances. So this plot I produced using the continuation toolbox that they produced in the paper that I cited. And if you come to the next page, on page 15, what you'll see here is a whole bunch of dashed lines, and I'm just going to label these guys. So the red dashed line is S33. The blue dashed line is S55. Green one is S77. Cyan one is S99. Magenta one is S1111. All right, so the dashed red line is the frequency of the second NNM divided by 3. The blue dashed line is that omega 2 divided by 5. The green dashed line is divided by 7. Cyan dashed line is divided by 9. And then the magenta one is divided by 11. And there are many more there still that I did not even plot. And so really, when I say you can get an infinite number of these, you really do get an infinite number of these. It keeps going. Now, in real systems that have damping, these higher order internal resonances tend to not show up just due to the damping. The damping tends to kill them. So something like an 11 to 11, if you could achieve that level of energy in your system, that kind of ratio will typically be killed by damping, or that internal resonance will typically be killed by damping. Now, if you're doing, killed by damping usually in a transient setting. So if we're thinking about transient responses, these higher order internal resonances will die out and not appear. In the case of like a forced response, you can still achieve those because the damping may not be able to overcome that resonance. It depends on your system, it depends on the damping, and so forth. All right, so here I've only shown these odd internal resonances. There are also even internal resonances like a 2 to 1, a 4 to 1, and so forth. These correspond to what are known as unsymmetric NNMs, and I didn't compute these. You can't use the numerical continuation tool. You have to use some other techniques to identify those. And so in the paper that I cited, they did do that for the 2 to 1 and the 4 to 1, and they only went up to a 5 to 1 in this case. But you can see that they still do exist and they show up there. You just got to do extra stuff to compute them. So it's not only odd, even though the nonlinearity is cubic, we still get even internal resonances as well. Okay, so in addition to these unsymmetric NNMs, you can also get NNMs that are represented by closed curves in the configuration space. And we're just going to briefly call those closed NNMs for simplicity, but it's not really standard. It's not really what people would call them, but we can just call that. So unsymmetric and closed NNMs are generated by bifurcations in the dynamics, and as a result of that, the actual continuation method that I've used to compute some of these NNMs breaks down, and that's why you've got to do other things as well. Okay, so in order to expand our NNM definition to include these internal resonance behavior, we are going to extend the definition. In this case, we are going to define an NNM, or nonlinear normal mode, to be a non-necessarily, let's say, non-necessarily synchronous periodic motion of a nonlinear system. Periodic motion of a nonlinear system. Okay, so they may be synchronous, they may not be synchronous. That's not really important to us. What really matters is that they are periodic responses. And by extending this definition, we can now account for the features of internal resonance and include those as being part of a nonlinear normal mode. Whereas with the Rosenberg definition, that definition breaks down for internal resonances, despite internal resonance still being periodic. Okay. All right, any questions so far? All right, we got a few more pages and then we'll be done today. All right, so the third fundamental property is that of bifurcation, mode bifurcations, and stability. We saw previously in example 3 that more nonlinear normal modes than degrees of freedom can exist. And as a result of that, not all NNMs can be regarded as nonlinear continuations of linear normal modes. Some of them fit quite nicely based on that, but others do not really fit along that. Especially if you can have many or more than one existing at the same time. Furthermore, NNMs can be stable or unstable, and which is in contrast to linear theory where all of the modes are neutrally stable, so they'll always be stable for all time. And in this case, when we say it's unstable, we mean that a small perturbation from of a set of initial conditions that generate a particular NNM will lead to the elimination of that mode. You'll get a branch hopping and you'll jump onto some other solution instead. Okay. Yeah, bifurcation and stability are interrelated concepts because change in stability occurs due to a bifurcation. We can take a look at the stability of the first NNM for that system we've been studying throughout this lecture on the next page. Here I've gone ahead and plotted what portions of the solution are unstable and which portions are stable. This is done using that numerical continuation tool, and they use a method known as Floquet analysis to compute the stability of these solutions. In this class, we are not going to cover Floquet theory, but all you really need to know is that you can use it to compute regions of stability. And one thing I wanted to point out is that if you zoom in on that subharmonic tongue, you'll find that right where the S33 solution touches, that portion is stable. So this S33 motion can be realized physically. Any of the red curves here are actually points where you cannot realize it because the motion is unstable. And in fact, what you can see over here, there's actually a portion where there's only a single nonlinear normal mode or periodic solution, but it's still unstable. So it doesn't even necessarily have to be during a resonance or on a tongue. You can have instability show up in other portions of the solution.
What does that mean?
It means that So again, real systems have damping in it there. And if you were to try to force along this point, you're going to jump most likely to like a second NNM, or you're going to get no response at all, or very weak, very low amplitude response.
And what does it mean when we have two stable solutions?
So in a case like right here, in this case, it can jump between the two.
It's like probabilistic, like it doesn't choose one, it just.
So if we're thinking of the case where you're forcing the system, it will depend on the initial conditions. And again, this is for Hamiltonian dynamics. We're not really considering forcing or damping in this case. So again, these are the backbones for the motion. And like we saw with the method of multiple scales, where the frequency response function wraps around the backbone branch, the same thing can happen here as well. Okay. All right, so fourth property is just the deformation of these frequency response functions at resonance. This is just a plot shown here. It's very hard to see that, but it should be easier on the video at least. If you compute the frequency response function for a linear system for a varying forcing amplitude, what you find is that they're all the same because it's a linear system, and by definition it should be the same. And then you could connect all of these by a single line, and that would then give you the curve in a frequency energy domain. If we take a look at and do this for a nonlinear system, you can see how these FRFs actually end up bending over, and the nonlinear normal mode for the free response ends up being at the tips of those. And if you connect all of those points together, you end up with the backbone branch from the frequency energy plot for the free response system. So another way, although computationally expensive, to compute nonlinear normal modes is to compute the FRFs for varying forcing amplitudes and plot along that, although computationally expensive. Okay, we got one more property, which I'm just going to state right here. These nonlinear normal modes are invariant. That means that if you initiate the motion on a specific NNM, the remaining NNMs will remain quiescent for all times, in the sense that if you excite only a single nonlinear normal mode, and again we're thinking of without damping here, so in that case if you excite only a single NNM, then all the other ones don't respond at all for all time. We're not going to go through the analysis of that, but you can demonstrate it using what's known as the normal form theory. Okay, we're going to take a look now at some different frequency energy plots, just so you guys can see what these things look like. So here is example 4. I'll write out the equation of motion for you. So it's a 2-degree freedom system. We're going to look at a couple different 2-degree freedom systems, and then we'll take a look at a cantilever beam as well. And so in this case, the equation of motion are x1 double dot plus 1.001 minus and that 1.001 should be multiplied by x1 minus 0.001 times x2 plus x1 minus x2 cubed equals to 0, and then x2 double dot plus 0.001 times x2 minus x1 plus x2 minus x1 quantity cubed equal to 0. So in this example, we have two equal masses that are coupled by a very weak linear spring and a strong nonlinear spring. Okay, and so here is the NNM computed again using that continuation approach. The two NNMs here, we end up with an S11 plus in black, and in blue is the S112. And we actually get a couple of different internal resonances, some that appear at low energy, particularly we have one right here, which is a 5-to-1 internal resonance. And again, it lines up with the S55 minus curve. And then we also have another tongue right here, which is the S31 internal resonance. I'm sorry, it's a 3-to-1 internal resonance arising from the S33 minus branch. And then later on at higher energy, you get another 3-to-1 internal resonance, and then you also get a second 5-to-1 internal resonance. And that's because in this case, at low energies, the first NNM is increasing its frequency while the second NN is relatively flat. And then later, at higher energies, the second NNM increases dramatically, then giving rise to these additional internal resonances. And it goes up further, and again, there are also like 2-to-1s and 4-to-1s that were not computed here. Okay, and the reference for this is down there. Let's take a look at another 2-degree freedom system. In this case, there is a grounding nonlinear spring and only a coupling nonlinear spring in this system. We won't write out the equation of motion, but I will give you the values of the parameters. So M1 is equal to K1, which is equal to K and L2. Those are all equal to 1. K and L2, 1 actually, K and L1 is equal to 0.5, and then M2 is equal to 0.05. So in this case, M2 is low mass, and we would consider it to be a local attachment, or in particular, this is called nonlinear energy sink. And if you compute,
And this is a third power?
yeah. Both of these are cubic terms. The KNL1 and KNL2 are both cubic, yeah. If we go ahead and we compute the two NNM branches for this system, the first nonlinear normal mode actually starts with an energy frequency of 0, and at low energies, its motion is isolated to the attachment. At low energies, the second NNM is isolated in the mass M1. And as we increase energy, several different tongues show up. First a 1 to 9, a 1 to 7, and then a 1 to 5, and a 1 to 3. And then more and more show up as well. And there's actually an additional branch, this S31, that appears. And again, this is kind of what we're talking about. You can have more than one NNM existing at the same time. Okay. There's a reference for that one. Here's a 2-degree freedom system with a vibro impact in it. And so what that means is that, again, we have a small mass. Lowercase m is small compared to big M. They're connected by some linear coupling stiffness K1. And the key thing here is that there is a rigid stop, a distance delta shown here. So when the relative displacement is equal to delta, there is an impact and then a sudden reversal in the direction of the velocities of the two masses. This is the strongest type of nonlinearity you can have in a system, and at least for a hardening type nonlinearity. And so you can think of it, if we draw a plot of polynomials. So if we start with something, we don't want a line, we want something like that, something cubic with a linear term. A quintic is then going to be something like that. So this is like x cubed, x to the 5th, x to the 7th. So when you have a hard impact, it is equivalent to an infinite power. So x raised to the infinity, into infinity. And in fact, the way you model it depends. You can either choose to use a clearance nonlinearity where you're modeling it as a spring with a very, very large stiffness, or you can do impulse momentum theory and do impacts. So when you have an impact, you stop integrating. For example, if you're doing this numerically, you would stop integrating, use impact equations to compute new initial conditions, and then start the simulation over until the next impact. Okay, and so for this system, you can compute a frequency energy plot as shown here. This was not done using numerical continuation. This is done using non-smooth functions and in a level of analysis that we won't go into in this class. And my point of showing this here is that this can get very, very complicated, and there can be lots of different resonances that can show up, and they can be unstable or stable, and the solution for a transient response with damping, for example, might start in one branch, then jump to another. You can't see a laser, let me draw. Might start here and then jump down, and then jump down, and then jump down. In fact, that's what the dotted lines actually represent, is a transition between these different resonances. So this stuff can get very complicated very fast. And this is still only a 2-degree freedom system with just the strongest type of hardening nonlinearity you can have. This comes from the paper shown there. All right, our last example is out of a cantilever beam. This is work that I've did previously. It's just a standard cantilever beam with a cubic spring attached to the tip of the beam. It's just standard steel, generic parameters. The material properties for steel, discretized using 10 Euler-Bernoulli finite elements. And the length, the width, and thickness are shown there as well. And here's what the NNMs ended up looking like. And this is a case where I could not compute the second NNM further than what's shown here in red. In fact, it just runs into stability issues. In fact, if you do compute a little bit further, it gets stuck on a branch and it just stays there for all time. That is a numerical issue, not representative of like physical reality. But again, you get all these different tongues and they show up in these different NNMs. Here I'm only showing the first 3, but I actually computed, when I did this research, I computed all the way up to the 9th NNM using this technique. And so they're all there, and they all have different types of internal resonances to show up, and you can then study those as well. We will use methods like the wavelet-bounded empirical mode decomposition to analyze these internal resonances from simulated signals as well as real experimental signals. Okay, and with that, we